here. Imagine, so we didn't get to sorting yet. I mean, you use sort right now, but we didn't learn how you sort yourself. But when you sort, let's say you have a list of numbers, and you need to sort these numbers from smallest to largest. Okay, one thing is you look at first element and you look at second element. And if the first element is bigger than the second element, what do you want to do? You want to swap them, right? Okay, so let's do that. Let's freeze frag out. This would be somehow basic operation in sorting is that you take two elements and swap them if they're out of order. Okay, so the code for that is simple. Imagine you have a, let me make sure I'm doing, okay, so the code for that is, let's say I have 100, A is 100, B is 1. I print them to make sure that really it's like that. And let's say now I want to swap these two values. Such that A is 100, B is 100. So how would you do that? This is simple, right? Should I do A is equal to B? If I do A is equal to B, then we lose what was in A, and we need to put it in B, right? So we should temporarily remember what was in A. Okay, so you can have some variable that remembers what is in A before you change A to B, and then you change B to temp. Okay, so this is a very routine way to swap two values, and let's see that that is working. All right, so let's check that we swap that. All right, so that works. Okay. But when you are doing sorting of a list, you are doing this all the time. You're going to be comparing some elements if they're out of order, and you swap them. So usually when you're using something all the time, you don't want to keep on writing these 5 lines of code. You want to make a function. Okay, so let's try to make a function that swaps for us. So we have a function, swap x, y, and then we do, so then we copy this solution, right? That's the solution that we want to do to swap the values. So we have temp is equal to x, x is equal to y, and finally y is equal to temp. So this is exactly the same swapping solution we did. And let's, now instead of doing swapping here, instead of doing the swapping here, let's call the function to swap for us. Okay, I'm going to comment this, and instead of that, I'm going to call swap to swap A and B, and then print A and B to make sure that it's swapped. Okay, does that work? It's exactly the same code. Okay? Why does it not work? Yes? Exactly. So it's the same reason that the previous example showed. Okay? So this is the reason it's not working is for exactly the same reason that the previous example printed what they printed. Okay, so let's run it. Let's draw it quickly again. What we're drawing by hand, this is what you should be doing when you're trying to understand this topic and when you're trying to answer these type of questions. Oh, thank you, thank you. All right, so let's run this. So we have here a main starts running. Okay, Python executes this to learn that the function swap exists, goes to the next line. On the right-hand side is an immutable object, so we said you might as well imagine that that value is stored in a variable in a case of immutable objects. We go to the next line, does the same. Right-hand side creates immutable objects, so we might as well imagine that it's stored in the variable. So here's your main, and we print it. It says print 8b, 101. That part is clear to everybody, I'm sure. Okay, so now we have a function call. There is a function call. So this function pauses. This one pauses. And function swap starts running. What is the first thing that gets executed? Sorry? Well, give me exactly the lines. Yeah, it is true. What gets executed?
The argument x.
This is parameter, yeah. Our x is equal to a and exactly. This is what gets executed. Don't mix it up and say a is equal to x. It doesn't even make sense. A is equal to x, but x is not defined yet. So what would you put in a? A and b we have already. Okay, so x is equal to a and y is equal to b. Let's execute that. What is stored in a should be placed in x. Okay, and x doesn't exist yet, so we have to create a variable x and place in it whatever is in x. What's in x? It's an integer 100, so we put that in x. What's in b? So now we are done with that line. X is equal to a. We have to do y is equal to b. Okay, y doesn't exist yet, so variable y of swap gets created. What should we place in it? It's whatever is in b. What's in b in this simplification is an integer 1. So here's what the picture looks like after the first line of the swap function is executed. Now we do the rest. Okay, so here it says on the right-hand side, whatever is in x, put it in variable temp. So variable temp doesn't exist yet, so we're going to create it. And remember, it's created. I'm putting it inside of the swap function because this temp variable is created by the temp function is running. It says whatever is in x, put it in temp. What's in x? It's an integer, so we might as well place that integer inside of the variable temp. So we are done with that line. Here we say whatever is in y, put it in x. So we already have both y and x. What is in y is 1. It says put it in x. So we put 1 in x. Then we have this line. It says whatever is in temp, put it in y. What is in temp is 100. It said put that in y. So we put 100 in y. So look what happened. We did switch x and y, but we never touched a and b. This is what we wanted to swap. Okay? And this function is now at the end. So the function terminates. So all of this is gone. So this swapping is for nothing. All right? So the control returns to the main. So main is not paused anymore. It continues running. So it's done with this line. Goes to the next line. It says print A, it's 100, print B is 100, nothing got swapped, so you get this result. Okay? Questions? Yes?
In order to get the swapping, would you have to print swap AB?
Print?
Swap AB?
No. Print none. What does that function return? Okay. So here, let's do that. Let's not guess. Okay? Print. So you are doing, let's say you are doing this, print. Okay. So what this print prints is whatever this function returns. What does that function return? None. It's not going to print that. It's actually going to print word none. Okay. All right. So that's not what you want. But let's now actually go back to the original problem that I actually said. It's like you have a list and you have elements of the list. And it's the elements of the list that you want to swap. So let's say in the simplified version, I really just want to swap the first and the second element of the list. So let's code this one. Okay, so there was that. So let's write a function def swap first 2. What do I have here? Oh yeah, let's say I have some list called A. All right, and let's again kind of mimic this solution. Not kind of, really mimic. And we want to swap the first and second elements. Okay, so we do temp is equal to A of 0. That's the first element of the list. Then I do second element should be equal, the first element should be equal to the second. And then I say the second should be equal to first, but we stored what was in first in temp. So here it is. So it's exactly the same solution. And now let's do this type of thing, right? We create in the main a list L that has two values, 100 and a 1, like here. Then we print that list to make sure it really is 100 and then 10. Then we do make a call to this function and pass it a list L. And then we print L. Okay, so it looks exactly the same as this. All right, so let's comment out this and focus on this thing. So we have a list. We printed before the swap and we printed after the swap. Okay, does it swap it? It does. It does. Again, for exactly the same reason that go back to the first example in fact lecture 10. Okay, so again, if you draw the diagram and follow what's going on, you will understand that you're actually changing the list. So let's draw that as a last example. Okay. So the main starts running, and it says on the right-hand side, create a list. Lists are mutable, you have to use an arrow. Okay, so and here we don't have a variable L yet, so we have a main that runs. Variable L gets created. What should be stored in it? Well, on the right-hand side is a list, so we cannot put, thank you. On the right-hand side here is a list, so we cannot imagine that the list is placed in the variable L because they are mutable, they are changeable. We have to use arrows, and we put a list here, 101. And we print L, it prints 101. Okay, so now this function starts running. So this one is paused. Okay, and this one, function swap first 2, starts running. Same question, what's the first thing that gets executed? An actual command. So tell me, what is what? A is equal to L, right? Okay, so we execute A is equal to L. So this function is running. There is no variable A yet. Okay, so we create a variable A and we figure out what needs to be placed there. Whatever is in L should be put in A. Remember, this is assignment operator. Whatever is in L, put in A. What's in L? It's an address of this list. Okay, so the same address should be in L. You simply draw an arrow to exactly the same list. So now both A and both L and A are the names of the same list. If you change one, you're changing the other. Okay? Unlike those integers that we were dealing with. Okay, now we do this. We say, okay, whatever is in A1, put it in variable temp. We follow, all right, so we follow A0. It said this is A0. It's hundreds in there. It's an integer. Variable temp doesn't exist yet, so we should be making it variable temp of this function here. Since this is an integer, we might as well imagine that it's stored in temp. We are done with that line. Then it says whatever is in A1, put it in A0. We follow A. A1 is here. A1 is here. What's in A1 is 1. It says put it in A0, which is here. So you're gonna put the 1 there. So that's after this line is executed. And you see here, L is pointing to that. We are changing L. Okay? And finally, this line here, what's in temp? What's in temp is 100. And it says place this in A1, lists are mutable. We follow A, we follow A1, and we place 100 in there. Okay, so we come to the end of this function. There's nothing else to do. Function doesn't return anything, so the function terminates. All of its variable, all of its space from the stack is released. And this function can now resume. It was waiting over here, so it's not paused anymore. And you see L has changed. All right, when we were changing A, we were changing L as well. And now when we print L, we swap those two values. Okay, is that clear? If it's not clear, please take these examples, take examples from lecture. Okay, so now I changed this to this, by the way. This is just a PS. It changes to this. What does this print? Does it swap the values? I don't see anybody drawing anything. Okay, they should be drawing this to figure out what's going on. Okay, let's see if I can draw you what happened. What's happening? New movie recording. I don't want to be in the movie. Oh, there it is. Okay. Okay, does it swap it? It does not swap it, okay? So again, if you draw the picture, be perfectly clear why it doesn't swap it. I will do this super quickly because basically it's just that one line that changes. So up to this point, when you execute this line, oh, I don't want presets. Okay, the picture looked like this when main was running. We have here 101. And then this function starts running, executes a is equal to else. So this one is running. Swap first two, creates a variable a and makes a go to the same list. But now we come to this line, okay? What does this do? You go to the right-hand side. It starts with what? The right-hand line starts with a square bracket. That means you're creating a list, okay? So you do that. You don't change the rule now. Whenever you see I'm creating a list, you create a list. So it's not this one, you're creating a new list. I create a list on the heap always. I create a list, says what should I put in the list? I should put as the first element of the list, whatever is in A1 should be my first element. Indeed, this new list has 1 in the first position. What should I put in the second place? I follow this list. In A0, it's 100, so I put 100 in that list. Now that the list is created, what do? Once the list is created, I send an address, put it in this variable. So this variable A does not point anymore to this list. Now it points to this list. Okay. Again, in Python, variables do not have loyalties. They're going to point to the last thing you told it to point to. So it's going to hold the address of the last object. So the picture looks like this. You changed A, but you never changed L. Okay? So now the function terminates. This is gone. You never touched L. Okay? The questions? You look super worried. It's like this. Okay. It really is all the same rules. Spend some time, redo all of. There is about 6 examples in total. Maybe 4 that we did in lecture 10. Well, not 6. 4 examples in lecture 10, 4 here, and maybe 2 on your lab. 10 examples that you can do in half an hour. Draw every one of them following this rule, and you will get this. Okay? And put it in Python Visualizer. Okay? All right. Okay, so we see that sorting is super important. It is super important, so let's finally learn how to sort. Okay. So, because we're trying to learn how to solve something and always solve it first conceptually, let's go back to the cards. You have a sequence of cards on the table facing down with numbers in no particular order, and you want to sort them. So you don't see them. The operation you like to do, at any one point you can open 2 cards, compare them, and then do something. Okay? And in fact, this is very actually adequate to what's happening in computing, because in general you're computing, at any one time you're computing 2 numbers. You're not going to compare 10 numbers at a time. It's going to cost you 10 operations. Okay? So you're comparing 2 numbers, you draw something, put them down, and open next 2 numbers. Okay, so let's say you have 1,000 cards lie down in sequence. How would you sort them?
process.
Okay, so here's a suggestion. I'm going to repeat it. So you look, open card 1, card 2, you compare them. If they're in order, you do nothing, you leave them. If they're out of order, so the first is bigger than the second, you swap them, okay, and then you close them down. Now you look at second and third card, you repeat the same procedure. If they're in order, you leave them. If they're out of order, you swap them. So first, second, second, third, third, fourth, fourth, fifth, until you compare the last two, okay? So we come and compare the last two. Are we done? No, we are not done. However, you can conclude something, okay? Think of what happens to the max. So when we go maximum element, when we go through the list once, where is the max at the end of this process? Can it be in the middle? How? Because when we come to the middle, we compare max to the next. We compare the middle, that's the maximum, to the next. They are out of order because this one is the max, so we swap them. Okay. So can it be next to the middle? If it's a max, I'm comparing it to the next. Max is bigger, so I swap them. So it means actually, when you think about it, that when you're doing this first pass, max is always moving. Especially think of it as being unique, but if it's not unique, then this one is max as well. Max always moves to the end of the list. So first time you pass through the list, by the end of your first pass, what you know, you don't know about the other element, but what you do know is that max is at the end of the list. In other words, the max is in the correct position. So in some ways, you can imagine that you don't even have that card anymore. Now you go through the list again until you come to the end. What do you know now? What happens to the second largest? Second largest now travels because the max, because this is now in the first n minus 1 element, that's the max, so that's the one that's going to travel to the end. So if so, after the second bar, second max goes there. By the way, here's your second solution to reporting the k largest. You go, you do this procedure k times, k largest will be at the end. This one's k times n as well. It's basically the same as that. So this sorting, so if you go n time through the list, by the end of n rounds, if you do n rounds of this, it will be sorted. This has a name, it's called bubble sort. Okay? And you're going to implement this one in the lab, I think. I don't know, I made labs maybe 2 years ago, so I didn't really look at them, I have to say. Okay, so that's bubble sort. Other ideas, how else could you solve this problem? In some way, what this does, it's almost like it finds the max, but in some, in an indirect way, it finds the max and puts it to the end. Then it finds the next max and puts it to the end. Okay. So, any other ideas of what to do? Yeah. Sorry. You said to find the max, put it to the end. I can't hear. Sorry.
Have
Okay, yes, okay. So you're already getting into implementation detail, but I think the idea is, and I'm going to switch it and talk about min because it's the same, because what I want to implement is the min. Okay, so you find the min. Where should the min be? You go through the list, you find the min. You find it somewhere. Where should min be? First, okay? So if the min is not first, I swap them. First and the min. So now the min is correct position. I never have to look at it again. So I have a list of size n, I find the min. If it's not in the correct position, I swap these two. Now the min is in the correct position. Now I start with a list. You can do that with your card, with the cards as well. Now I look from the second card, because the min is in the first position, in the correct position, I never have to look at it again. I go from second card to last. I find the min, and what do? I swap them with the second position. If the min is not in the second position already. And you repeat. Now the list starts from 3. So you repeat that until you end up with a list of size 2. You look at the last two guys and you swap them if you need, and then you're done. Okay, that's called selection sort. Okay, so let's implement that. And let's look at it actually I have a few slides on it. Here. Okay. So here, in the beginning, you have a first whole list. You find a 1, and it's not in its place, so you swap. You swap where you found the 1 with whatever was in 1, and we end up here. It's better that I show it here. Okay, so 1 and 2 swap. So now the minimum is it's in position. We now look at the list starting at position 2. We find the min. Min is not at the beginning of this sublist, so we swap and 2 and 9, and we end up with a list like this. Okay, we find the min here. Min it's not at the beginning of this sublist, so we swap min and whatever was in the first position. We end up with a list like this. So we are working now with this sublist. We find the min, it's a 5, but 5 is in position, there's nothing to do. Okay, we change the sublist now to this one. We find the min, it's not in its position, so we swap it with the first element of the sublist. Okay, so that one is in position now. And now finally we have a list of size 2. That's the last time there's something to do, because if their list has a size 1, like this one here, so it's sorted. Okay, so the last time there's something we do when a sublist finally has size 2, and we find the min, it's 8, it's not in position, so we swap them. Okay, so let's implement that. That's called selection sort. Okay. Are there questions about these? Okay. All right, so we're going to implement selection sort. Okay. So, def we have a list L that we want to sort. Okay, so input is a given list L, and we want to sort L. So type contract is L is a list, and we want to sort L. What's the return type? Okay, so I heard many list. It's not list. We are not returning a list. It's a none, and I heard some none. That one is correct. And let me show you, this is very important, so I'm going to make a pause here. It's the input list that you're sorting. You're not returning some new list that you sorted. It's the given list that you're sorting. So you're not returning anything. The one that you gave me, you're sorting. And in fact, Python itself has 2 implementations of sort that differ by this. Whether you want to sort the given list, or you want a copy of that list that is sorted, that depends on your application. If it's somebody else's list, you better don't sort it. Maybe they don't want it sorted. Then you better make a copy of your list and sort the copy. So let's look at Python's own implementation. So let's look at this. Okay. Let's have a tiny list that is not sorted. 2, 10, 1. Okay. So let's read help pages. Python has 2 of them. One is called sorted. It's in built-ins. Sorted can sort all sorts of things, right? So it looks a little bit strange, iterable, but iterable just means a sequence, okay? But let's read what it says it does. Return a new list containing all items from iterable, read iterable as a list, containing all the items of the list sorted. So it returns a new list containing all the items of the iterable sorted. Okay. So let's run this. So we want to do sorted on L. And this function says return something. So let's capture what that function returns in some variable x. So when I look at L, is L sorted? L is not sorted. What is x? So else is a new list that has exactly the same element as L, but it's sorted. Okay, so sorted creates a new list that contains the copy of elements and sort them. Let's look at the second version of sorting that Python have. It's in a module list, and it's called sort, not sorted. It doesn't have enough words, But important thing to notice here is none. It doesn't return anything. It sorts L. That means in place means it sorts L itself. Okay, so let's run this one. L dot sort. This one is in list module. You call it in object-oriented way. That means with a dot operator. And let's see if this function actually returns anything, and if it does, what it returns. We're going to capture that in variable y. Okay, now L is L sorted. Now L is sorted. Okay, the function dot sort from list module sort the given lists. What's in X? What about X? What's there? Sorry, I mean Y. What's in Y? Thank you. It's none. This function doesn't return anything. None is in Y. Okay? So there's a big difference between the two, and the one we want to implement, at least because I'm asking you to implement that one, is the one that sorts L itself. Therefore, the return type is none. All right. So let's first write down what are the steps, and then we're going to code step by step. Okay? So we have steps in English. We are repeating that procedure. Remember the procedure again. You have some sublist. I find the min in the sublist, and if needed, swap with the first element of that sublist. Okay. So the first step is find. We repeat this. Find minimum in sublist L, starting in position I, and we go to the end. Okay? Notice that unlike in binary search, this I always moves by 1 to the right. Okay? You put the minimum position, next sublist, you just go to the next tile. Next sublist, you just go to the next tile, where the beginning of the sublist is. End is always the same, beginning moves by 1. Okay? So find the min in the sublist. Okay? Next step, swap L of I, that's the first element of sublist, and the min that you found if needed. Swap these two. That's your algorithm, and you repeat this. Okay, we'll see how you repeat it. So let's code these two steps at least. Okay. Find the min in a sublist. We know how to. We have a list starting in position L of I, and we go to the end, and we want to find a minimum. Remember, typically minimum you found as follow. You have some current, you assume the current minimum, let me call it min current, is you assume is the first element of the list. The first element of the list is L of I, because list starts in position I. Then you go through the rest of the elements. Let me do this for J in range. This is just a variable named J. We go through the rest of the elements. That means we start at position I plus 1, and we go to the end of the list. And we compare current min. If the current element we're looking at, L of J, is actually smaller than the current min, we need to update the current min. Because L of J is smaller, that's your new min. Okay, you know this, we've done this on several occasions. Okay, so we are done with this step. Now we have to do the swapping. And we learn how to do the swapping. And we actually said this is the important stuff of many, important element of many, how do you say this, sorting algorithms. Okay, so we save the first element of the list, because this is where we will write the current min. The current min, minimum current element, the minimum should go in this position L of I. Okay. L of I should be, because that's the first element of the list, should be current min. Okay. And we should put temp is whatever was in position L of I. Where should I put it? So I should put temp where? So we said we have list starts at position I. We go through the list, we find the min somewhere. So min goes in the first position, but this guy should go in its position. So what should I do there? Can't really do anything. Well, I can be searching where did I find that min. But we did all of that work. I do sometimes things like this just to indicate it's much better to think first. What do I need? not only do I need the min, but more importantly, I need to know where that min is in order to do the swapping. Okay? So when I was looking for the min, I should have keep track where I found the min, because that's where I should place the element that was in the first position. So let's redo actually this minimum such that what it does, it remembers where you found the minimum. Okay?
There's no pointers in Python.
Everything is a pointer in Python. So basically, what's the index of the minimum? At the beginning, it's I. Before we even started, we assume the first thing is the minimum. So it's I. But once we find the smaller element, if we find a smaller element, then we update where we found a min to what? To J. We found it in position J. Okay. That's it. So basically, now here I should say, where should I put a temp? I should put it in position, what should I put here? That's where min was found. Oh, sorry, not min, min index. Wherever you found the min, that's where you put temp, which was the first element. Okay? We are done, except that we have kind of extra unneeded things still in this min. Do I even need this? If I know where the min is currently, do I need to store the value of the min? If I know the position of the min, what's the value of the min? How do I get the value of the min? L of that position. So I don't even have to store this minimum. If I know the position, then I know so I can get rid of this. And here, when I'm at, okay, in this particular position, I need the value because I'm doing comparison. But I know the value. It's L at min index. That's the, and I don't need to update this. All I have to update is the position. Okay, so we coded everything. All we have to do is figure out this repeating. Okay, so what should we be producing here? This loop should be producing sublist. We should be looking sublist. I should be 0, so the sublist is 0 to the end. Next I should be 1 to the end. Next I should be 2 to the end. So I should be going from 0 to, let's figure out what. Okay, so for I in range, except that now I should move this, I hope. That's the last thing we have to do. Ooh. Sorry, it goes like, see, you can do mistakes when you do such silly things. Okay, so let's make some space here. So this loop here finds the position of the minimum element. This part here swaps the first element at the position of the min and puts the min in the first position of the sublist. And we repeat this. What should I put here? Let's go back to this picture. So I, in the beginning, that's the first round. These are the rounds of your loop. Here's what your loop is doing, starting from the top. So in the beginning, I is 1. That's your whole list. Then in the next round, next time you enter the loop, I is 2, I is 3, I is 4. These are the positions. The positions are 0 in the list, I is 0, I is 1, I is 2, these are the sublists. I is 3, I is 4, I is 5. When should I stop? So I start with 0 as the beginning of the sublist. And what's the last sublist I should look at? So I goes from 0 to what? Exactly. We should go here until len of L minus 2 actually. That's the last value you want to take, because that's the last time list has more than one element. That's the last time there's something to do. If there's one element, there's nothing to swap. You just leave it. Okay, so basically we are done. We just go to len. Last I that we want to take is len of L minus 2, but the range goes up to that value, so this means the last value R we will take is len of L minus 2. Okay, so that's your selection sort implemented. Okay, every time you enter the loop, you're looking at the list starting at position I to the end, you find them in. If it's out of place, you swap with the first. Now first is in a position, so next time you enter the loop, the sublist you're looking is from the position I plus 1, so I moves one more. Okay, any questions about that? Okay, so let's see. We said that the best algorithms for sorting do, so this list, say this list, L, has n elements. So len of L is L, n, as always. N is the number of elements of the list. Oh, by the way, don't be confused that here I'm not testing is minimum out of place. Because if minimum is really the first element of the list, this really does nothing. Okay? It takes the first element and puts back the first element. So it's not wrong. We are doing it for no reason, but it's not wrong. Okay? All right. So we look at this. It has n elements in the list. How many operations does this do to sort? Is it one of those best solutions that does n times log n operations, roughly? This is n squared, okay? So it's far from n log n, very far from n log n. Let's understand why this is n squared, okay? So let's learn first how to remove noise from this, okay? So let's try to, it's much easier to analyze this once you remove the noise. What do I mean by that? You're going to recognize it then. Okay, so this thing here, focus on the loops, unless you have a line like that uses in or calls another function. Then you have to worry, oh, does that in cost me linear? And a function call may cost me more than 1. But we don't have anything like this here. We have here, this one just remembers index, this one if statement. This is all one operation, this one, this one, this one. So when you go through these lines, the only thing that matters are these 4 loops. Really everything else is one operation. And it's, let's say 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. So it's going to be 6 times at most, however many times these loops are executed. So let's focus on that. So let's do something here on the side for the purpose of counting that's going to help you. We look here. We first have this loop. You see, that's the beginning. That loop says for I in range. And we have here len of L, that's n minus 1. Okay? Because we are trying to say this does at most one operation, I can ignore this minus 1. Okay? So I'm removing the noise, if you like, for the purpose of counting. Then we have another loop here, and what that loop does, it says for j in range I plus 1 n. And then imagine we are removing the noise and replace it with print star. That's why I'm asking about these print stars. Okay. So this is the same. This thing and the above, when I ask you how many stars this print is the same as the one above. Okay, these two things do the same roughly number of operations. Okay, so let's see, we got an answer already that this is going to print roughly n squared stars. Let's understand why. Okay, we can even do this one exactly. Let's do it. So when I is 0, you come in here, this is 0 plus 1. 0, that's 1 to n. So first time you enter the loop, you print 1 to n, you print n minus 1 stars. Okay, because we go from 1 all the way up to n minus 1, that's n minus 1. Okay, so when I is 0, we print that many stars. When I is 1, we come here. 1 plus 1 is 2. We go from 2 to n. and that's n minus 2. That prints n minus 2. Okay, we come back in. Next value I take is 2. So we go here, 2 plus 1 is 3. We go from 3 to n. That prints n minus 3 stars. Okay, and so on. I hope you can see the pattern that this goes down by 1. So we can do dot, 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 plus 3, plus 2, plus 1. So this does actually exactly this many operations. Okay? You need to sum this up. Okay? But because all I need is an upper bound, I want at most, I'm going to add one extra n to help me solve this equation. So this is now not equal, now this is less than. So we do less than this. I added one n. How much does this sum to? Surely somebody knows. But I'm going to show you, hopefully, something that you will never forget because it's so wonderful. I hope you're going to appreciate it. And it was this. So the story goes like this. I don't know if I mentioned this before in this class. Did I tell you about how Gauss solved this when he was apparently 8 years old? So here's how the story goes. He's considered the best mathematician ever lived, meaning across all history. Okay? I think he lived about 200 years ago. And the story goes, he was in first year primary school or second year, and the students were loud and not listening, and teacher told them, okay, everybody quiet, sit down and add first 100 numbers, thinking that's going to make them busy at least, I don't know, 20 minutes. And apparently 30 seconds later, Gauss raises his hand and gives the correct answer. Okay, so here's what he figured out. So we have here n numbers, 100. In his case, it was 199 plus 98 and so on. Let's say we're going to pair these numbers, first and last, then second and second to last. So we're going to pair them up from outwards in. How many pairs are we going to create, first of all? If you have n numbers, how many pairs are you going to have? N divided by 2. So let's now, first of all, see what these pairs add up to. We do n, so we do first 2 outside 1. We get n plus 1, right? Okay, we do next 2. What do they add up to? We have next to our n minus 1 plus 2. That's n plus 1. Okay, we do next 2. We have n minus 2 plus 3. What does that add up to? N plus 1. In fact, one goes down by 1, one goes up by 1, so they always add up to n plus the same amount. Okay, so you have n plus 1. You pair them up, you're summing them. Every time you get n plus 1. But how many times how many pairs do we have? N times 2, n over 2. So you get that the sum is, in fact, exactly. This sum here is exactly, because she asked exactly. She didn't say approximately. It's n over 2 because you have that many pairs times n plus 1. So let me write it like this because it's more readable. Okay, so this is equal to n times n plus 1 divided by 2. Okay? So hopefully from now on until forever, if somebody asks you what's 1 plus 2 plus 3 all the way up to n, how much is that? You'll know that this is n plus 1 times n over 2. And what does this have to do? We said that that's how many operations does our solution do, roughly. Where is the square? Where is the quadratic? Oh, this is n squared divided by 2 plus n divided by 2. Okay, and so this is for us what is important. And this is n squared divided by 2 plus n divided by 2. We say erase the constants. You're going to get then, if you erase the constants, you're going to get n squared plus n. And you keep the bigger term in big O notation. N squared is bigger than n. So you get that this is actually n squared. Okay? So when you're doing analysis, try to get rid of the stuff that is not important and do analysis like this. So the one above is basically equivalent to this one. And this loop is executed roughly n squared times. So this is n squared solution. So this is not a good one. Okay? So in next class, we're going to learn about the fastest, one of the fastest, all the fastest one are n-log n. We'll learn one of them. It's called merge sorts. Okay, so see you Monday.